Dynamics. This is class 3. We're still doing kinematics of particles. Today we're going to deal with projectile motion and relative motion. But first, we're going to cover some things that are going to set up for the next 2 classes, right? So you can think of these next 3 classes, including today, as being related to each other in talking about the kinematics. We're going to deal with 2 dimensions, where so far we've only really been dealing with 1 dimension. Now we're going to, something could go back and forth or up and down or whatever. But now it can go up and down and left and right. So today's really rectangular coordinates is really what introduction is. And the next class will be, I believe it's polar coordinates, and then we're going to do path coordinates, right? So those are the 3 days. Today's rectangular coordinates. But there's a bunch of stuff in this class right here that we need to do to be able to set up for those next 2 classes. So today's going to be jam-packed full of stuff. Couldn't figure out a way to spread it out more evenly, but so we won't get through everything in class. So some of these videos are going to be very helpful for you to come back and look at. So like I said, we're going to talk about rectangular coordinates and some concept stuff that we're going to have to use later. We're going to cover projectile motion problems, which you probably covered in physics. They're really important problems, and sometimes people might be think that they're too easy and not pay attention to them. But you can make projectile motion problems that are more complicated and can really frustrate you. So we want to make sure we get some practice in those. And we also want to do relative motion here, right? But now it's going to be in 2 dimensions, so we're going to have to use some vectors. So there's a lot of stuff to cover today. So make sure that you put the time in to absorb all of this. For the equation sheet, this is the section that we're looking at. It's really a lot of this is the same, but make sure we notice that there's going to be vectors going on here because we're going to be in 2 dimensions. So just as a review for vector math that you had in statics, right? If we're going to deal, let's just start with position vectors. Go back to position vectors. And note that in 2 dimensions and rectangular coordinates, we have a position vector, which I doubled down and not only made it bold, but also put this little arrow on top, give it a hat. Can be broken down into coordinates x and y, where the unit vectors, which remember, they just tell you what direction it is, and they have a magnitude of 1. All right, so this is the x direction, is the I, and the y direction is j. Now, in the other coordinate systems, we will often take a e, lowercase e, and then have a subscript for it. So we could, if we were to be consistent with those coordinates, that coordinate system, other coordinate systems, we would have an e to the x and an e to the y as the unit vectors right here. And if you're going to add 2 vectors together, you can either use triangles or components, right? And the triangles are good, but I think that they're better. They're more suited as a confirmation of some work that you're doing. We could always break any vector down into its components and in whatever coordinate system we happen to be using. And in the rectangular, we break it down into x and y, and we break both of them down. We can add the 2 x components together, right? And we add the 2 y components together, and then we get the new vector. So that makes it nice and simple and easy to do. Okay, so that's just a little bit of a review. Now, this is sort of like a derivation, but it's also to try to convince you of the necessity, of the importance of doing some of this, the vector mindset in dynamics, right? So let me open up. I forgot to open up my. Let's see. How do I do it? Oh, I go over to here. Okay, camera. I gotta turn my document camera on. All right. See if he's gonna turn it on. Come on, document camera. You can do it. Come on. All right, there you go. All right. So, in the handout notes right here, we see that if we wanted to get, okay, so let's say we started with a hypothetical where we have 2 points, right? And then we started at a point P, and then at some later time, we go to P prime, right? And the distance between those 2 points is going to be this delta S, right? So we can, in looking at this, right, if we have the average of velocity, and that delta s, well, that delta s is going to be the arc length. My bad. The delta r is just going to be the distance between them, right? So we could say that delta r is equal to r minus r prime, right? That's the idea right there. That's the vector triangle that we're looking at right here. But we want to say that, like, between those, if we take that time between there, right, we could say that it's delta r over delta t, and you're noticing that it's still a vector. And then if we take the limit as that gets smaller and smaller, which will make it mean that the points get closer and closer together, right here, we would see that the average velocity would be delta r over delta t, and as that delta t starts to get smaller and smaller and smaller, we'll see that we have the velocity right here at that point. Now, the really important thing to note right here, the bottom line, the big takeaway, is velocity is always, we'll even capitalize it, tangent to the path. And that's a really important concept. That's like the main thing that this right here just showed, right? That how is it tangent to the path? Well, you see, it isn't quite tangent to the path here, but as we got smaller and smaller, it became tangent to this path right there, right? And they didn't do a great job of drawing the path right there. But this right here is tangent to the path that this thing was following. Okay, but now if we go to acceleration, right? So we're going to take that acceleration thing, and we're going to find out a couple big takeaways, right? So first off, now let's take two velocity vectors. There's a velocity vector at p and a velocity vector at some time later at p prime, right? And so if we were to like make a triangle out of this, right? So now we have a delta v. I don't know why this turned to q and q prime. I can't remember what their logic was, but anyway, they're saying like, okay, well, let's take some other time, maybe later on this one. I think this was, well, because, well, I guess that point kind of looks like that point right there. So they're trying to make some kind of delta v that's going between them. As you got smaller and smaller, right, this thing would have the acceleration would be formed like this right here, right? It would be sort of over into this direction. And something they haven't pointed out here maybe clearly is maybe these vectors, well, this vector right here maybe is longer than that vector, right? So what we end up seeing is we have a velocity, an acceleration that is not tangent to the path. And what we end up finding is that we actually have two components to this, right? There's a component right here that is tangent to the path, and there's going to be one that's going to be coming in there, right? So that's just, by the way, that's just one way of breaking this thing down. But we're going to have this component, and this is going to be like in the path coordinates that we're going to see this, where this is the change in speed. Well, this is going to be part of this acceleration is going to be due to the change in direction. And we're going to see that that's the centrifugal acceleration, right? So the big takeaways here that are like unlike velocity. Acceleration is not tangent to the path. Acceleration is not always, maybe, is not exclusively, is not exclusively, I decided to say exclusively, exclusively tangent to the path. Why? Because change in direction. Contributes to the acceleration. There's also change in magnitude too. Change in magnitude also contribute. Sorry, that's what I wanted to write. And I don't know if it's worth writing all these things out, but I do this in class sometimes. So more of it, we're going to have more of this in the next class, but the big thing to understand is that we're going to have some other, we're not going to be tangent to the path. That's basically the idea, is for acceleration, whereas velocity is always tangent to the path. Now we have probably this, I think maybe I'll end the video after this next sheet right here. Here is some stuff that we need to do to set up things for next time, right? We need to take a derivative of a velocity or a vector function. We'll take a generic vector, right? So like, and this could be the reference coordinate system. Something we might need to know that a reference coordinate system can change with time, right? It's quite often it'll be its position or even its orientation might change with time. And when that happens, we need to be ready for that, right? So if we just take some a generic vector, right? And so say that we have in one case we might have like some scalar function, right? There might be something. Some number that doesn't have any direction multiplied to something that does have direction, right? So f is just some scalar term, right? And it can change with time. F can change with time. It can be some function of time, and it's being multiplied by a vector, right? And which is just some vector, right? So like maybe the p is just some point, some vector that looks like this. And then we just took some quantity maybe and multiplied by it, which would have the effect of either making it longer or shorter, right? It's just some scalar number. And both of these can change with time. So if you take the derivative of them, and in this case, I guess we decided to take it, this could be just some generic thing. We could make that time on the bottom if we want. But it's just a derivative with respect to some other parameter right there. That we would have d of f times du and multiplied by the original, right? So we want to take the derivative of this, and now we have to do this. This is the product rule, right? I'm going to write that down, product rule. As a consequence of the product rule, this has to be true, where we take the derivative of this first part and multiply it by the original, then we take this first part and multiply it by the derivative of the second part. And once again, this could be time, right? That little u. Or it could be some other parameter, whatever it is. Okay, then we could also take, when we want a derivative of a scalar product, now we have two different vectors where q is also a vector, right? So it would be like qx, and in rectangular, it would be this, right? When we're dealing with rectangular coordinates today. I said p. That was dumb. Qy. And I guess I decided to keep it as three-dimensional, right? So we usually do a 2 dimensions just to keep things simple, but it can be, all these things can be extended to 3 dimensions. So if you take the derivative of this is of course dp and then du times q, and then plus, and I think you need to dot. We still need to keep the dot in there, in the dot product, yeah. And then the p dotted with the q du. And this is sort of meaningless stuff until you start like applying it. And it's not meaningless, but it's just it's not as interesting. But we'll get to the application of it sure enough. I always think of these derivations as being something that's like kind of like, yeah, take your medicine and then you can go ahead and use it for something practical, but you have to kind of pinch your nose now and just swallow this, and then get to the stuff where we actually use it. And if you take the derivative of vector product, you could probably see where this is going. It's all the product rule. Basically, we just wrote down the product rule, right? And that you need to consider what happens with all of the parts, because they might, all of the things might change with time. So now if we go ahead and go back up to the top right here, and let's just go ahead and take this vector right here and take the derivative with respect to time. right? So this was just a generic thing to remind ourselves about the product rule, and that we have to make sure that if anything changes with time, we have to keep that in consideration. But now we'll just do, this will seem kind of trivial because we're doing it with rectangular coordinates, and we'll see that it's not trivial for the other kinds of coordinates, right? This is the setup for all of that. So if we're going to take dp with respect to t, right, we should have to do all three parts, or all three things, right? So we go dpx dt times I plus px, no, darn, don't do that. Not a hat. This is just the magnitude of the I. Sorry about that. Di, making stray marks. dt. Then we go to the next part, and we go dpy dt j plus py dj dt. Plus, I think I'm okay here. I forgot him. dpz dt times j, nope, k. Wow. I'd restart this video, but because I'm messing up. It's early in the morning. It's like 8:45. I didn't have my second cup of coffee yet. pz and then dk dt. But that unit vector I, j, and k, right? In rectangular coordinates, we just set it there. We just plop, it's there, right? It could shift around, it could translate, but it's not going to rotate, right? So and the unit vectors just establish what a direction is going to be. So it doesn't change with respect to time. So all of those terms go away. So you could say that dp dt is just equal to dpx dt I plus dpy dt j plus dpz dt k. So, and this is just only only in rectangular coordinates. It's not going to be true in other coordinate systems, because almost every other coordinate system has some, at least in some portion of it, changes with respect to time. And so all of these go away. So we have the special circumstances with rectangular coordinates that the derivative of a vector with respect to time is just the derivative of all of the components individually. That makes it a fairly simple and straightforward a method of figuring things out and figuring out the derivative of stuff. But it ends up making it seemingly more complicated in path and especially polar coordinates. So I think, no, let's continue some more with this because it's boring stuff, right? So we can make, let's not make a separate video for this, because I have a feeling not many people will watch this first video or will hang in for very long. And there's only a little bit left onto this. Okay, so if we say that we have the velocity, right? We know that the velocity in 2 dimensions. We're gonna stick with 2 dimensions right there. Of a position vector, right? And the position vector, you'll recall, is just going to be the coordinates of the location of the thing, right? Well, that coordinates, the location of the thing is going to change with respect to time. So we need to take the derivative of this. And we just simply end up with velocity is equal to dx dt I plus dy dt j. Or if we wanted to, we can go x dot I plus y dot j. Somebody might write it that way. I don't know. And then acceleration is simply I think I got lazy here and stuck with the coordinates, the dot notation. If we do that right there, it ends up being hat, right? It's got me double dot because we've taken the derivative of them, and it's just the components where we have the derivative. I think this is just a summary down here, right? And just to give an idea that we want to make sure that the coordinates that we might find. I mean, this curve might be in space, right? But it'll still be tangent for the velocity. The path might be crazy, but the velocity right here, v, as you're seeing right there, is going to be still tangent to the path because it's always tangent to the path. The acceleration here, and I'm not sure I agree with the vector that they chose to put in there, because one thing we're going to find in path coordinates is we're going to find that the change in direction, the acceleration due to the change in direction, is going to be towards the center of the arc of curvature. So they're drawing it this way, and I think maybe it would have been better this one another way. So that's the end of this video. Like I said, this is set up for other things to come, and I think it helps to contextualize why we have other components to consider when we're using different coordinate systems, especially when it comes to the transverse, radial and transverse coordinates, which we also call polar coordinates, right? They have extra terms, especially in acceleration, and we want to know why and understand them and digest them. So some of this taking the derivative of those helps us to understand that better. And I'll see you next. For the next one, I think is projectile motion, which is going to be sort of a review, but it's also we'll do some examples and hopefully see that it's actually a little more complicated than you might think.